Hey, so hopefully you guys were able to do assignment number 3 successfully. And assignment 3 from programming point of view perhaps was a little more involved because even though the main concepts were very straightforward, meaning what we were doing is we were creating an architecture for programming neural networks. Okay, where if you recall, what I did is I created a class called layer to represent one layer of neurons. And the idea was that doesn't matter, we wanted to create a 1 layer or 2 layer or 5 layer neural network, we can easily create that, right? So the layer class represented one column of neurons. We decided how many neurons are there, right? And then we also created a class called network, where we can specify as many layers as we feel like it by indicating how many neurons will be in the first layer, how many neurons will be in the second layer, third layer, and so on, right? Then the layer class itself decided on the activation function. For example, whether we will use a sigmoid or tanh or linear, and so on. So it also had storage for storing the delta, which is, remember, the loss up to the derivative of the loss up to the middle of the neuron, right? And that's what we call the delta. Okay. So because once we have defined the delta in all the neurons or calculated the delta, then, like I said, it's very easy if there's weights connecting from one layer to another, then the delta, for example, if I call it delta 1, delta 2, so what's the relationship between delta 1 and delta, or for example, what is partial L over partial, let's call it W1 in our example. So what is partial L over partial W1? So as you guys saw, the relationship is whatever is the input that connects to the neuron. So if this input, for example, is called A1, then that will be, for example, A1 multiplied by the delta 2, right? So because delta 2 already has the derivative up to this point, okay, then to get to this point, we just see which previous input connects to this particular neuron as an example, right? So deltas make our calculation of the derivatives and the back propagation extremely easy. Okay? So please do not unmute. Okay. So anyway, the other concepts that we discussed in assignment number 3, let me quickly recap so that I can describe the next assignment to you. So the other important things in assignment 3 were, for example, we talked about the gradient descent algorithm and a few different variations.
Hi, Professor. Hello.
Yes.
Yeah, hello.
Do you have
Professor.
a question or no? Okay, so the other things that we discussed in assignment 3 were the gradient descent algorithm. And this is the main training algorithm that we use in training neural networks. And the fundamental idea, if you remember, was if theta is representing the weights and biases of our network, then as we go into our training loop.
Excuse me, Professor.
Yes.
Sorry for the disturbance. Like, you know, why my data was slow, I don't know. I just opened my canvas. The status was absent for me.
Email me and I'll try to manually add that to you.
Thank you so much, Professor. Thank you so much.
Professor, that's the same issue I have faced.
Same thing. If anybody did not do the attendance in time, just email me and I'll mark it manually.
Sure, thank you.
Okay, so the main gradient descent algorithm, if you remember, was theta equal to theta minus lambda, which is basically our learning rate, multiplied by the partial L over partial theta. So, for example, if one of the weights is W2, it will be W2 minus lambda partial L over theta. This is annoying. Okay, please do not unmute yourself and keep and talk to each other. So, talk. Okay, so coming back to the gradient descent algorithm. So we have three variations of the gradient descent algorithm. Okay, one of them is just the regular gradient descent algorithm. So one of them is the mini batch, and one is the full batch. Often we just, and one is the regular gradient descent algorithm. And what's the difference between all of these? So here, per training input, because remember, we need training pair data. So we need an X, which is our input to our network. What is the expected Y? So this is the expected output, I mean. So we have a lot of these training data when we train our network. For example, in assignment number 3, you were using the Moon data set. And what we did is we created 200 training pairs as an example. We could have done more, we could have done less. Okay. The more data we have, the better the network trains according to the data, right? So we had 200 XY, we called it X0, X1, because those were the two inputs. And Y, whether it belongs to the red category or the blue category, was our expected output. We use 1 and 0, 0 and 1, right? For the Y part. Okay. So in the regular gradient descent algorithm, what we do is we pick one of these inputs. So for example, if this is our training data, let's say instead of red and blue, let me put O's and X's over here. So if we pick one of these as an example as the training data, okay, then based on this input, we will feed it through our neural network where the weights and biases are randomly initialized. So then we'll go back and we will apply the update, theta equal to theta minus lambda partial L over partial theta. So per training, we will do the update of the weights and biases. So that's the normal gradient descent algorithm without any batch being involved. So that is the regular gradient descent. Okay. So then this does not work as well through a lot of our empirical, the the testing that we have done over many, many data sets, many neural networks, we found that if for every training we keep adjusting the weights and biases, what happens is one of the training data will say, okay, increase the, for example, value of W. Another one will say decrease it. Another one will say increase it, decrease it. So it does not produce as good of an answer because some of the examples may not be, they may be noisy or so it does not create as effective as good of a learning if per training item XY pair, we adjust the weights. So in the mini batch, what we do is we say, okay, let's compute the gradients for a mini batch. Okay, let's pick the batch size over here, for example, to be, let's say, 8. Okay, that means we'll feed through our network. So through our network, we will feed. So in our, so let me draw a picture and to clarify the mini batch. Okay, so if this is our network, doesn't matter how many layers we have, this is the input. This is our output produced by our network. Suppose this is our Y, the expected output. And then we have some kind of a loss. And here's the L, right? So in the mini batch case, like I said, for example, we'll pick X0, pass it through, and suppose it produces some loss. We'll go back. We will create partial L over partial theta corresponding to this X0 input that we fed, and we will store the value, okay, in some temporary variable. Then we'll pick another data item. Okay, suppose we pick X1 from our training pairs. We again will feed it through our network. Create some more room here. Okay, we'll again feed it through our network. Okay, compute the loss, compute the gradients, go back, compute partial L over partial theta, corresponding to the second input, X1. And now what we will do is we will go add this to our previous partial L over partial theta, which was corresponding to the first input, right? So same way, we will feed in X7. Then again, we'll compute the loss. We'll compute partial L over partial theta, meaning derivative with respect to all the weights and biases. Okay, and then go over here and add it to our total partial L over partial theta. So as you can see, the partial L over partial theta was computed 8 times, corresponding to 8 inputs in our example, right? So then how will we update theta? Okay, do we do theta equal to minus the learning rate? Learning rate, if you recall, is fixed, for example, 0.01, right? Multiplied by partial L over partial theta. So which partial L over partial theta do we use? Because this value is the sum of everything, right? So should we use the sum? And the answer is rather than using the sum, what we will do is we'll divide it by how many times we computed it. So you can see this is the average gradient. So that's how the average gradient will be used to update the previous value of the weights and biases. Okay, so again, through our experimental work over the many years of these neural networks and deep learning architectures, we have determined that the mini batch works the best, so produces best results. best learning results from training point of view. Okay, so then the question is, what is the batch size? Okay, so the batch size, should it be 8, like I gave you in this example, or should it be 4? Should it be 16? Usually we have it powers of 2 as we talked about it, because in the implementations, the computers are designed based on binary arithmetic. So power of 2 usually works better, but you can use batch size of 10 or 12. It doesn't have to be exact power of 2, right? So which batch size works better, okay? And the answer is, if you have a lot of data, and again, it depends on the data set itself. So if you have a lot of data, then typically anywhere, for example, for image type of data, so anywhere from 32 to 64, or sometimes even 128, you will get the best learning results, okay? And how do we decide which one is the best learning, okay? So let me also clarify that. So if we go back to, let's say, assignment number 3. So let me briefly bring the assignment number 3 over here. Where did it go? Okay, so assignment number 3. Okay, so remember we were experimenting with different number of neurons in the hidden layer, and we were creating a 2-layer. For your own learning, try creating a 3-layer network, 4-layer network. See, does it do any better job, or does it do the overfitting? Okay, so how do there's a very important concept that you will run into a lot. So we briefly talked about it, but because it is so important, let me clarify this one more time. So overfitting is where the definition is where the neural network produces good results on the training data, but produces much worse results on test data. So anytime you see this, for example, let's say you are doing a classification problem, okay? You are trying to have your network recognize, let's say, 10 different types of images, like some images may be cats, some images may be dogs, cars, planes, ships, whatever, right? So if you have 10 classes over here, and suppose your training data is 10,000 images, 1,000 images belonging to each class, right? And during training, suppose it keeps getting better and better, and it gives you 92% accuracy during training, right? Then let's say we have 1,000 data, which we do not give it to our neural network during training, but this is our test data of 1,000 images, 100 images belonging to each category, let's say. So after it is trained, we will do the testing on the test data and see what is the accuracy, because this is the data the network has not seen, okay? So now if it produced 62% accuracy, so that means whatever we did over here, the architecture we picked over here is too complex. It's overfitting the data. It's memorizing the training data, but it will do, and that's what I mean, it will do a poor job on the test data. So ideally what we want is, we want the test and training accuracies to be very close to each other. Usually in practice, the test data will always be a little bit less, which is okay. So for example, if it is on the training data is 92%, on the test data, if it is 89%, this is okay, okay? Because like I said, there will be a difference. There will be a slightly less accuracy on the unknown data. But if the difference is relatively large, for example, 92% on training data, 80% on test data, to me, that is still overtrained or overfitted model. So we need to go back and either train it less or make the model less complex, okay? And the example I was giving you in overfitting was, you know, suppose you have a linearly separable data. There are a few noisy cases over here. Okay, let's say it's X's and O's, okay? And let's say in reality, you know, some of the data is noisy, meaning this is the noisy data. We know by the nature of the problem that a straight line would be able to separate it. Now, if you use a very complex 10 hidden neuron network and it's trying to come up with this kind of boundary, right? So that decision boundary is severely overfitting it because it's trying to accommodate each and every training data, right? So even if we draw something straight in one of these O's over here, this O over here, even if it is wrongly classified during training, that's okay. Now we know in the test case, as we do it on the test data, it will do a good job, okay? So I forgot to enhance the enhance the assignment number 3, but let me give you an optional exercise. For your learnings. Okay, so in assignment number 3, what was our training data size? Okay, if you recall, it was 200. Okay, we created 200 points, and each point we know whether it belongs to the blue or the red category, right? Okay, so what I'd like you to do is, instead of using 200, create data of 400 size. Okay, then after you create data of 400 size, split it into 200 for training and 200 for testing. Let me see, there were some chat messages. Okay, someone is waiting outside Dana. Okay, whoever is waiting outside Dana, they can maybe go to the security and ask them to open. Oh, you got it. Okay. Oh, it was you. Okay, all right. Okay, so coming back to our optional exercise that you will do for your own learning is you will create a data of 400 size. You'll split this data into 2 parts, 200 for training and 200 for testing, okay? Then you will train only on the 200 training set, okay? So the 200 size that you already have split the data in 2 parts, just train it on this one, okay? Then test accuracy on the 200 test set, okay? And okay, and your goal is to determine the best model. in terms of number of neurons in the hidden layer. So do 3 neurons in the hidden layer produce the best accuracy on the test data? Because remember, we want highest accuracy on the test data. So this is always our goal. Okay, this is always our goal. Highest accuracy. It doesn't matter how accurate you are on the training data, nobody cares. Okay. The unknown data, how does your model perform on the unknown data? And whichever model, in our case, we are creating a 2-layer network. So the number of neurons in the output is fixed, right? Because we are producing in 2 categories, red and blue category, either it's 1, 0 or 0, 1, right? From output point of view, it's how many neurons do we want to use in the hidden layer? As you guys saw in assignment number 3, let me quickly show it to you. So if we use 3 neurons, this is the type of decision boundary it produces. And see, in assignment number 3, this accuracy, is this accurate indicator of the performance of the model? Yes or no? Okay, the answer is no, because we didn't split it into train and test. We are measuring the accuracy on the same data. So this is really the training accuracy, okay? So 98% is meaningless unless we have some data where it hasn't seen what is the accuracy, right? So anyway, I was explaining through pictures that, for example, if we use 30 neurons, here's the 30 neurons you can see, right? Then this is the decision boundary it creates. When it creates these, a little bit of these curvy things to accommodate individual data, that is an indication of the overfitting of the model, okay? And you'll be able to verify it once you split it into train and test data. How many neurons? I guarantee you 30 neurons will not produce the highest accuracy on the test data, okay? Because in the test data, the blue that is appearing somewhere over here, it may be somewhere over here, right? And so it will take, these may be red in the test data. So it will end up making it far worse than it is, right? So anyway, this would be good for your learning point of view. Okay, so because overfitting is such an important concern, and there's no solid theory that we can rely on to say, hey, use this many neurons for this particular problem. Okay, it's mostly, based on experience, based on, little bit of experimentation. So if there's a new problem, you will try to take a look at. So typically what we do is we take a subset of the problem and try to see, maybe we'll run a small model to get a feel for it. Is it a very difficult decision boundary between the different classes? Okay, if it is producing very, very low accuracy, as an example, on the small subset of the data, okay, and we created a medium complex model. And if we are getting very low accuracy, that means, oh, this is a very difficult problem. The decision boundaries are very complex, and perhaps we need to come up with a more sophisticated model. So then, like I said, we will experiment. Again, we can't make the model too complex because then it will end up overfitting. So with some experience, with some trial and error, you'll be able to come up with the proper model which does not overfit and produces high accuracy on the test data. Okay. There are some techniques that we do use, okay, that I mentioned to you. And one of them, we also actually, two of them, we used it in assignment number 3. So techniques to prevent or minimize. I should not say prevent because that, again, if you pick too complex of a model, you cannot, there's no guarantee of prevent. I mean, nobody can say for sure, oh, it does not overfit. Okay, we can minimize the overfitting. And two techniques that we used in assignment number 3, one of them was dropout, and one of them was weight regularization. Okay, so these two techniques are very popular in designing neural networks that we employ, so that even if by accident we picked a slightly more complex model, these two techniques will safeguard against it and have it still do a really good job on the test data. Okay, so what was the idea? Let's go over it briefly, both of these techniques. So what was the idea behind dropout? Okay. By the way, I don't know if you guys saw that the Nobel Prize was announced last weekend. And one of the Nobel Prize winners was Geoffrey Hinton from University of Toronto. And he's known as the godfather of AI, right? And the dropout technique was proposed by Hinton. Okay. So you can see, and it's an amazingly simple technique. Okay. So the idea, as you saw, was if we are creating, let's say, some layer neural network, okay? So suppose we have 100 neurons over here, 50 neurons over here, 10 neurons over here, right? So in the dropout, okay, so first of all, dropout is never applied to the output layer. Okay, it is always applied to the hidden layers. Okay, so these are called the hidden layers, if you recall, in our terminology. And this is our output layer. So what we do is we go to the output of the hidden layer neurons and zero them out randomly, okay? So if we have 100 neurons, we pick a dropout rate. So for example, the dropout rate could be 20% as an example. So what we will do now is we will go out of these 100 outputs that are being produced, okay? One of them may be producing an output of 0.2, 0.15, and so on. Okay, so we'll pick 80, or we'll pick 20% of these. 20% if the dropout rate is 20%, 20% of outputs will be zeroed out during training. So same way, if we have, so 20% of 100 is 20, right? So we'll pick 20 and 20 neuron over here, randomly select them and zero them out. Okay. Part of our learning is also becoming better in programming, right? So how will we code the dropout? As you guys saw in the previous assignment, and I forgot to clarify it, but in Python, hey, we have sorry, what was it called? There's a binomial distribution, which is available to us via NumPy. I think it was np.binomial, right? And then what we will do is we will say 1, comma, 0.8 as an example. Then if I wanted to create an array of, so suppose I call it Z, okay? So Z equal to np.binomial 1, comma, 0.8, and suppose I put 100 over here, okay? So what that means is, give me 100 numbers, okay? So Z will be 100 numbers, or an array of 100, okay? And most of them will be 1, 1, 1, somewhere 0, 1, 1, 0, right? And so out of these 100 numbers that we have, so these 100 numbers, randomly 20 of those will be zeros, okay? So then if I store it in a variable called Z, then all I have to do is go to the output. If the output is, let's say, was produced in some variable A1, then I can say A1 equal to A1 multiplied by Z, okay? So you can see wherever the 1 is, it will leave that value as I multiply for as 0.2 before, it will stay 0.2. If it is 0.15, excuse me. So if it was 0.15, then again, if the corresponding Z value is 1, it will stay 0.15. But somewhere over here, let's say the fourth value over here, suppose this is the fourth value, was 0.32, okay? So as you can see, we're multiplying it by 0, so that will get zeroed out as it flows forward, right? So to implement dropout from programming point of view, you will create a binomial distribution. It's based on the dropout. If the dropout is 20%, you will use 0.8 over here, so that 80% of them will be kept 1. The 20% will be zeroed out, okay? And then here, this could be 1D data. So this is really the shape of the data. It could be 100 by 10 as an example, 100 by 1. Okay, so now if you go back to your code, you'll be able to see how the dropout was implemented in the code. So usually we don't change the dropout rate per layer. So if there were multiple layers, same way for these 50 neurons, again, 20%, if we selected 20% as the dropout rate, 20% will be zeroed out during training, okay? We do not use dropout during testing. Testing, this will be not used. We won't be zeroing out the outputs because then it will be terrible. So dropout only is used. So dropout is not used in testing. So make sure your code is not applying the dropout at the test time. So if you change the assignment number 3, as I mentioned to you in the exercise mode, take the dropout out, okay? So you can create for example, a global variable as train or test. So if the mode is test, do not multiply this thing over here, multiply by Z, okay? So this is how you will do this optional exercise, okay? The second technique that I mentioned that helps us in minimizing overfitting is the weight regularization. And here the idea was very simple, and the idea was our loss function is whatever the loss function is, whether it's cross entropy or y minus a square, right? We also add another parameter over here. We can call it beta, or we can call it, so this is our basically, again, this is a parameter, just like we had the learning rate. So this is a parameter to control the contribution of this term over here. So again, this will be typically very small, for example, 0.001. Okay, so remember the idea was we want to minimize the loss as we train our network. Okay, so when will for the loss to be minimum, as you can see, the actual output has to be very close to the expected output. And this is why we are adjusting the weights. Okay, and also, so this term has to be small. So that's our training goal. And for the loss to be minimum, this term also has to be small, right? And as you can see, beta is a constant. So the only way this could be small is if the value of the weights is as small. So we don't apply the regularization to the biases. We apply it only to the weights. Okay. So if the, so this will be small if weights are small in magnitude, meaning it doesn't, positive, negative does not matter. And that's why we have the W square, okay? Because even if it's a negative number, the square will be always positive, right? Okay, so now as we go partial L over partial W equal to, sorry, theta equal to theta minus the learning rate, partial L over partial theta, right? So as we do now partial L over partial theta, okay, so for example, now theta is like weights and biases, right? W's and B's. Okay, so if we are applying it to adjusting the weights, take a look what will happen. Minus lambda, partial L over partial W, right? So if you do partial L over partial W as an example, right? Whatever this term is, this is the normal term, because remember, we'll go, if this is our network, somewhere over here is, let's say, the W coming out of one of the layers as an example. So we are going partial L over partial W. So we will go partial L over partial A over partial this, right? Until we reach the actual. So there will be some normal terms over here as we compute the partial L with respect to partial W. But what will be the effect of this term over here? As you can see, this will become 2 beta W, because the derivative over here is, so in our weight update, you will see if we make it 0.5 over here as part of the loss function, then 2 and 0.5 will cancel. So then I don't need the 2. Then beta, which is a constant, for example, 0.001. So as we do the weight updates, you will see this will keep getting added to the value of the weight update. So if you go back to assignment number 3, you'll see, oh, why were we adding this, small term over there? Because the whole idea was we want to minimize the loss. So coming back over here, we want to minimize the loss. And again, only way this loss will be less is if the magnitude of these weights is as small as possible. The smaller the weights, then it does not cause the network to have wide fluctuations, and whatever learning it does works a little bit better than on the test data as compared to the trained data, right? Okay, so those two are, once again, the dropout and weight regularization are the techniques to prevent or minimize overfitting, okay? And so as you do the exercise, you are already using the dropout, you're already using the weight regularization in assignment number 3. But further, you can still have overfitting despite the fact you're using those techniques. But like I said, they don't eliminate it, they minimize the effect of it. Still, if you pick too complex of a model with 30 neurons, you'll see it will not perform as well as on the test data as compared to the training data, right? Okay, so now let's come to our assignment number 4 that you will do this week. And hopefully, see, first time you go through these assignments, you know, like I said, assignment 3, for those of you who have a little, you know, not as strong of a Python background yet, may find it, you know, what is this object-oriented layers, and, you know, how are we connecting them together? Okay. Even though you got it to run, you may not fully feel 100% confident yet, but don't worry. As you keep going to assignment 4, assignment 5, okay, I'll recommend come back over here as your knowledge keeps getting better, and you'll see, oh, it's starting to make sense now, okay? The first part of learning is being able to recreate and understand it. Then second part of learning is you have a new problem. You will go back and use part of the code from your previous assignment and to implement this new unknown problem. And gradually, with more experience, you say, oh, I don't need anything. I know how to do it. Okay, but that takes time. Okay, so don't expect you to be able to creating these networks and solving unknown problems. Okay, by the end of this deep learning course, if you're able to understand and copy paste part of the problem to solve a new problem is the goal. Okay, after taking, you know, reinforcement learning or advanced deep learning or natural language processing would be the goal. Oh, after the middle of the course, yes, I give you a new architecture, you'll say, oh, yes, I can program it. Okay, anyway. So coming to assignment number 4, okay, in some ways you'll find assignment 4 a lot easier, okay, than assignment number 3, because I said, okay, let me just remove the object-oriented requirement. And let's just create more practical example. So assignment number 4, what we will do is, there's a very famous data set called MNIST. It's a digit recognition data set. There are a few data sets in the neural networks, deep learning domain, which are standard, okay? So MNIST, if I remember correctly, there's an, you know, just like we talked about Hinton being the godfather of AI, there are 3 godfathers of AI, okay? One is Hinton, one is LeCun. He was previously at, I think he works for Facebook now, but he was previously at NYU. So if I remember correctly, LeCun created this in 2005 and first time showed the convolutional neural networks, how they are so much better than, for example, regular neural networks, okay, in recognizing these. So to this day, anything we create, we often test it on MNIST to see how good it is, okay? In the early days, if you got, 90% accuracy on it, it was considered great. But now I'm pretty certain we have 99.99% accuracy with our new model. So it's an easier data set from that perspective. Okay. So in the original data set, there are 60,000 images. These are black and white images. So I'll show you the real picture in a second. So for example, these are handwritten digit images. Each image is 28 pixels by 28 pixels. Okay. So remember, a pixel is a dot. And in a black and white image, we use typically 8-bit resolution, meaning 8 bits to represent each dot. And 2 raised power 8 is 256, which means the value over here will vary 0 through 255, because the highest number you can represent which is equal to 255. Okay. So we have 0 through 9 as the different images. Okay, so 60,000 images are for training. 10,000 images are given to us for testing. Okay. So we'll create a model, we'll train it on 60,000, and then we'll test it on 10,000, okay? Because many of you are running these initial examples on your laptops. So 60,000 will take a while for it to train. So what I did is I randomly selected 1,000 images. So in your assignment number 4, you will not use 60,000. You will use 1,000 images for training, so that in a short amount of time, you can train your network, okay? However, you'll test it on full 10,000. Okay, to see how good your network is, right? And after assignment number 3, we've already discussed that as we implement our neural network, we'll be using the matrix forms of computations as we implement the forward pass and the backward pass and the back propagation, right? Okay. Assignment 4, you will use as you program it, you will use the weights being represented as a matrix, the actual outputs being computed as a matrix, even though it's a column. So if you have, let's say, 100 neurons over here, right? The output, as you can see, if I call it A1, the shape of those will be 100 by 1. Okay, so you can think of it as a vector of 100 values. And in matrix form, the vector is basically number of rows times number of columns. So because it's a single column, each output is, so you'll see this is how it will be, right? Okay, we talked about, for example, let's go to the next layer. Suppose we have 50 neurons over here. So in the previous lecture, we talked about what is the weight matrix that will connect the two. Okay, what size will it be? Anybody remembers? So 100 by 50 or 50 by 100? Okay, remember our terminology was we will go output number of outputs time the number of inputs, right? Okay, so since there are 50 outputs in my example, the weight matrix that we will create will be 50 by 100, right? So let me quickly show you to save time. Let's go to assignment number 4. Okay, so from the picture, hopefully you'll be able to see. Okay, so first of all, our input is coming as 784 by 1. Okay, because right now we are, whatever networks we are creating, they are column of neurons. Okay, so that means the input also, even though an image is like a two-dimensional data, image also has to be converted into a single column as we feed it to our network, right? So if we take a look at this 28 pixel by 28 pixel, right? Suppose the first value over here is 78. The second pixel, let's say, has a value 49. So what I could do is I could assemble all of this. So I start with the first row, I put 78 over here, 49 over here, right? And same way, if I keep going, let's say the 28th number in the first row happens to be 13. So then I can go 13, right? Then I go to the second row. Suppose the first number is 27. So then after 13, I can put 27. So row by row, I can just keep going, keep going, keep going. Suppose the very last number is 128 or 127, doesn't matter. 127. So as I put all of these pixel values into a column of numbers, as you can see, 28 by 28 is 784. So this image over here, all the numbers in the image can be represented, all the pixel values can be represented as a 784 by 1 vector, right? So if you take a look at the assignment number 4, the input, which we term as typically X, is coming as 784 by 1. Okay. Now, another thing we do is typically, so what will each one of these vary from? Because they are pixel values, right? They will vary from 0 to 255, right? So what we can do is we can divide each one of these by 255 so that the numbers vary from 0 to 1. So some may be 0.02, 0.035, 0.37, so the maximum will be 255, which will be 1, right? So typically we scale our inputs so that our inputs, rather than being 0 to 255, are 0 to 1 range. So this is typical practice in creating networks for any kind of classification. Okay. So let's go back to the architecture. So input comes over here, right? Suppose we'll create 2 layers because, I also, sorry, I already mentioned, because this is a digit recognition example, right? How many neurons will it be in the output layer? 10. So you can see this is fixed. There has to be 10 neurons. Whichever neuron has the highest output, that neuron, that is the digit it's recognizing. For example, if the 6th output is the highest, which digit is it recognizing? 5. Right? Because the first one is 0, the last one is 9. So if the 6th output is the highest, then it will be 5, right? Okay. Okay, so let's see if we agree on the weight matrices over here and the bias vectors over here. Okay, so if we decide to use 100 neurons in the hidden layer, what will be the size of this W1 matrix that I am calling here, W1? Okay, remember it goes by output size, input size. So there are 100 on this side, right? 100 neurons. And what's the input size? 784. So the weight matrix has to be 100 by 784, right? Okay, then suppose it goes through, there will be a summation produced over here. This is called S1 over here. As you can see, I call the sum, right? Then as it goes through the activation function, I called it A1 as the actual output because this is layer 1. And there will be some vector representing the biases, okay? So my question to you guys is, what will be the size of the B1 which represents this first layer? Because everything now, from now on, will represent as matrices and vectors. See, each neuron has one value for the bias, right? And how many neurons are there in the first layer? 100. So as you can see, it will be 100 by 1. So B1 will be 100 by 1. Okay. What about S1? There are 100 neurons. Each one is producing one S value. So it will also be 100 by 1, right? What about A1? 100 outputs, so has to be 100 by 1. So can we represent the forward pass and figure out what will be A1 then? Okay, so let's take a look. So we have 100 neurons. Our input is coming as X, let's say 784 by 1, correct? Okay, the weight matrix, which we called it W1 over here, what was the size? 100 by 784, okay? And S1 is the, so in terms of matrices, how will S1 be computed? Can I say, for example, W1 times X plus B1? Okay. Now let's see, as a matrix equation, is this satisfied? It's the matrix multiplication proper, right? So what's W1? 100 by 784. What is X? 784 by 1. So as we multiply these two, what will be the answer produced? 100 by 1. B1, we already agreed it's 100 by 1. Can I add 100 by 1 with 100 by 1? Yes. So what will be the size of S1? 100 by 1, right? Because we already talked about the sum, which is the middle of the neuron, is there 100 neurons, so it has to be 100 by 1, right? Now, as we go through an activation function, okay, suppose the activation function is a sigmoid, right? So remember, it goes like this. This is our S1, right? And this is our A1 in our example, and there are 100 of these. Okay, so first of all, we need to remember, we at the same time as we write on a piece of paper and we say this equation is proper, the next question is, how will we write it in Python, this equation, okay? Suppose the W1, S1, X, and B1 have already been declared as NumPy arrays of these sizes, okay? So then how will we write in Python S1 equal to, how do we do, because this is a matrix multiplication. Anybody remembers how we do that in Python? NP?
NP dot.
NP dot, okay? And then W1, comma, whatever our input variable is, okay, plus B1. So it's easy, right? Okay. Okay, now what about A1? How will we compute A1? Okay, so remember what was the formula for sigmoid? It was 1 over 1 plus e to the minus x, right? Okay, so anyway, so again, this is very easy. We can say A1 equal to S1. So when I say x over here, what I meant is in general, this is the f of x. If x is the input, then the sigmoid produces if the input is called x, it will be this, right? If this is sigmoid, what is the input going to it? S1. So it will become S1 over 1 plus exponent of minus S1, right? So anyway, this is how, and this could be NP dot EX. Okay. This is how easy it is to compute the forward pass through first layer. And same concept for the second layer. So if we go to, okay, let's go to the second layer. If we decide, well, not decide, this is fixed, 10 neurons in the second layer. So what will be their W2 matrix? 10 by 100, right? Because 10 on this side, but the 100 are coming from the previous layer. So this has to be 10 by 100. What will be the size of B2? 10 by 1. What will be the size of S2? 10 by 1. A2? 10 by 1, right? And then the expected Y will also be 10 by 1. And then if we, depending on the loss function, whether we do the cross entropy or the mean squared error, we can easily go through the second layer, compute the loss. So remember, our training always goes in 2 phases, receive an input from the training data, send it forward through the network. Once you have computed the loss, then go backwards and apply the gradient descent algorithm and update the weights and biases. So again, to simplify computation of the backward pass and upgrading the weights and biases, we can always compute these deltas over here. Okay, so suppose we do a mean squared error loss, right? So then this loss over here will be 0.5. In this example, it would be Y. See, we are calling this output coming out of these 10 neurons as A2, okay? So Y minus A2 square, right? How will we do now partial L over partial A as an example? Okay, partial L over 2 and this cancels. And as we discussed, this will be minus Y minus A2, correct? Okay, so then to compute delta 2, we further have to go from A2 to over here. So if our activation function is sigmoid, my question is, what will be, see, this could be represented as partial L over partial A multiplied by partial L over partial S2, right? Because S2 is up to the middle. This is, okay, so my question is, this we've already computed as minus y minus A2. As we went through the forward pass, we already know this, right? Okay, what about this second part over here? What's the value of this? Okay, remember for sigmoid, we said it is, let me refresh your memory. Okay. If this is S, and if this is sigmoid, and if we are calling it A, then partial A over partial S, which is the derivative of the sigmoid. Remember, we had found it as A multiplied by 1 minus A, okay? Or in general, if f of x is 1 over 1 plus e to the minus x, we said partial f over partial x is same as f of x, 1 minus f of x. So if we are calling the output, which is the f of x, as A, then it is A times 1 minus A. And I had given you an example. Suppose we do a forward pass and A turns out to be 3. Then what will be the value of when we go backwards, partial A over partial S? It will be 3 times 1 minus 3. Okay, see, that's why we picked these activation functions to be such that their derivatives are extremely easy. They can be described in terms of the value of the output. Okay, so coming back over here, my question is now, what will be the partial L over partial A? We already know is equal to minus y minus A2. Okay. Now, second part, partial A over partial, this is A2, this is A2. What is partial A2 over partial S2? Won't it be output is
1 by 1 plus e power.
It will be
minus
output
2.
as A2, right? A2 times 1 minus A2. Okay. So anyway, same way you can go compute the partial L over partial W2. You can compute the delta 1 partial L over, right? Okay. So as I mentioned, okay, as part of assignment number 4, okay, I'm saying show the matrix equations for the back propagation. So what is delta 2? I already gave you the answer for delta 2. Okay. What is delta 1? So hopefully, just like I gave you the answer for delta 2, you can go backwards and do partial S2 over partial A1. Then, so let's take a look at what is the equation for example, S2. Okay, in terms of the matrix equations, remember, what will this be? This will be W2. And what is the input coming from the previous A1, right? Is this proper from matrix point of view? What size of W2? This is 10 by 100. What size of A1? Uh, 100 by 1, right? So can these be multiplied? Sure. So that will give us 10 by 1, right? And of course, plus which one? B2. Okay. So now to go from here to here. because to compute delta 1 is the derivative up to the middle of the neuron, right? So as you can see, what is partial S2 over partial A1 then? Just W2. Okay. So in other words, delta 1, how is it related to delta 2? Whatever the weight matrix that connects them together, that's all we have to multiply. So it is simply multiplied by. Okay, so the question is this right? Because once you write these equations on a piece of paper, that's the way you'll program them, right? So what's the size of delta 2? Delta 2 is these values in the middle of the neurons. How many neurons are here? 10. So it is 10 by 1. What is W2? 10 by 100. Can I multiply these two together? No. So this is not right. Right? So you can see this is incorrect. So what is the equation for delta 1 then? Okay. What if I write as, sorry, W2 first, then delta 2? Okay, so what is W2? 10 by 100. Sorry. Okay, how about if I do this? W2 transpose. So then this will become 100 by 10. This is 10 by 1. Okay, so then you can see, sure, now what does this come out proper? Right? So you can see when you try to compute deltas, transposes will be needed. How do we compute the how do we write the transpose in NumPy? NP
Dot T.
Yeah, dot T also works, or you can say dot transpose. Okay, so so anyway, I just in case for those of you who are new to programming, I also gave you the code that you can examine on the second page. But for your better learning, don't take a look at the second page first. Okay. From just like I did in front of you, here's the network. Try to write the equations and make sure in terms of matrices, they are matching, right? So whatever I say, give me equation for delta 2, delta 1, then the gradient with respect to delta 2. So let's talk about, for example, so delta W2, when I write it over here, okay, what I mean is I'm asking you to give me partial L over partial W2. That's the meaning when I put inverted triangle. So in the math, the inverted triangle is a derivative, okay? So what will be the value of this, okay? So if you take a look at this picture, W2 is over here, right? So remember, how is it related to if you've already computed delta 2? How is partial L over partial W2? Okay, remember we talked about that is basically this delta 2 multiplied by where the input is coming from. Where's the input coming from? A1, okay? So what I'm saying is partial L over partial W2, which is same as delta W2 is, how is it related to this delta 2 will be multiplied by A1, okay? So it will be delta 2 multiplied by A1. Before you write it on a piece of paper, again, check from matrix point of view, is it proper or not? So what is the size of delta 2? Yes, 10 by 1. What is size of A1? 100 by 1. Okay, so no, that does not sound right. What do we want in this case? Okay, what is our goal over here? What's the size of delta W2? See, what's the size of W2? 10 by 100, right? So as you can see, that if there are 10 by 100, meaning there are 1,000 weights over here, then there should be 1,000 derivatives over here. Because remember, we'll be doing, so what I'm trying to say is, okay, to implement the back propagation, we'll be doing W2 equal to W2 minus partial L over partial W2. So what is the size of this? 10 by 100, okay? So what I'm trying to say is we cannot subtract the matrices. What should this come out to? It has to come out to 10 by 100. If it's not, the math will not work. Okay, when we add or subtract matrices, both matrices should be exactly the same size. So we already know W2 is 10 by 100. So partial L over partial W2 has to be 100, right? So as we put on the picture, okay, there are two components involved, delta 2 and A1, to compute the partial of, with respect, partial L over partial W2, right? So the only way it could work is, take a look, how could I get 10 by 100 as I multiply these two? What should I do? I want the answer to be 10 by 100. Exactly. See, if I did the transpose over here, okay, then you can see this will be 10 by 1. And transpose will make it 1 by 100. So now matrix point of view, this is satisfied, and the answer will be 10 by 100. Okay, so hopefully you know how to compute delta W2. Same way you can calculate what's the relationship of derivative with respect to B2. So if we go to B2 is over here, how is B2 related to delta 2? Okay, because remember from here, we'll go from here to here. Then from here, we'll go to here, right? This is S2. So what I'm saying is, what is partial S2 over partial B2? Okay, if anything that is not B2 is treated in this equation as a constant, and there's only one B2, so this is 1. So what does that mean? Then partial L over partial B2. So if I write it over here, partial L over partial B2 is same as partial L over partial S2, which by definition, what are we calling this? That's delta 2, right? Then we are multiplying it by partial S2 over partial B2. Okay, and what did we just found out? What is this? 1. So isn't the partial L over partial B2 same as delta 2. Okay. So to answer this, then this is really the answer is delta 2. Okay. So now you can go and further, compute partial L over partial W1 in terms of deltas, and then partial L over partial B1, okay, in terms of deltas. So part B is easy. Then you will program it. How do we read the data set? So first of all, what you will do is, let's go back to the data set. Okay. Okay, if you go under the handouts, okay, last semester, or the one of the previous semesters when I taught this course, this particular assignment was number 3. In your case, it's number 4. Okay, so the last link over here, you'll see MNIST data set in bitmap format for assignment 3, but it was, maybe I'll change it to assignment 4. So what you will do is from the handouts, download this zip file. Okay, as you download this zip file, extract it to a folder. So let me show you. As you extract it to a folder, for example, I extracted it on my D drive under this MNIST data folder. Okay, then further, there will be a data folder. If you go further data, you'll see 3 subfolders over here, training 1000. So like I said, these are the images that there are 1000 images. Let me see if I can show you one of these images. How do I view it better?
Zoom it on.
Open with, let me see. Let me see if I view it in Paint, what happens. Zoom. Oh, bottom. Yeah, you can see this is, for example, the image of a 0 as an example, right? Okay, so the way the each one of these file names are, for example, if you take a look at, here's a picture, what's the file name? 636.bmp. So can you guys guess what the first digit represents? If the file name starts with the number 6, that means it's an image of a 6. If the file name says 0, it's image of 0. So this is how, because remember, as we train our network, right, we have to know the input data. So if it, let's say, is some kind of a 7, so there are, as I mentioned, there are 600 images for these different types of 7s. As an example, some may look like this, some may look like this, right? So each one of them has a file name. So the file names will start with the 7. For example, this could be 723.bmp. Okay, so how do we know, as we are reading the file name, what image it belongs to, what category it belongs to? Like I said, the first number will tell us the image category. So the Python code that I've provided to you, what I'm doing is through the folder I'm looping through, I'm reading the file name and extracting the first, whatever the first number is, and that is my expected output, the Y category, the class for this particular image, right? So that code I've already provided to you. How do you read an image? So let me go back. Okay, so assignment number 4. So, okay, so if you take a look over here, the second page, I'm providing you the code that you will be typing in a file called where did I say? Okay. Yeah, I didn't. But anyway, here's the code to read the images. Okay, so you can see first in the beginning, okay, I'm creating two-dimensional arrays to read the pixel values for the images, or three-dimensional arrays. Okay, so if you take a look, train equal to np.empty 1000, 28, 28 d type float 64. So because why it's 1000 by 28 by 28? Because the MNIST digits are 28 by 28, and how many are in our training data? 1000, right? So train Y is 1000 by 10 by 1. And why is it 1000 by 10 by 1? There are 10 categories of images. Okay. And because in our training, there are 1000 images, and then, we will create 10 by 1 output, because output from our network will be 10 by 1. So the expected output should also be 10 by 1. And so this is to store all the expected outputs, right? Test and test Y. How many test images were there? 10,000. So you'll see this is 10,000. So that's straightforward. Okay. Then, like I said, I have a separate folder given to you for all the training images. And if you take a look, Y equal to int a file name of 0. As I mentioned, the first part of the file name tells us which image category it belongs to. So then for that position number, we'll set this to 1, because in the beginning, when we created the Y, it was initialized to all zeros. So only in that position where the image number is, if it is belongs to image 7, 7th position will set it to 1, all the others will stay 0. So in other words, what I'm saying is the way we are creating our training data is the expected output. So if the input is like 7, the expected output will be 1, 2, see this means 0, 1, 2, 3, 4, 5, 6. This will be 1, 8, and 9. Okay. So the 10 numbers, the 10 by 1 output that we are creating only will have 1 in the position which corresponds to our input, in this example, 7, right? Okay, let me go for 5 more minutes, then I'll stop for today. So anyway, I'm using the OpenCV library. So what you will also need to do is install, hopefully you've already installed. So let me show you, okay, in case I forget and down the road, you need to install another Python library, right? Okay, what you will do is you'll go to the command prompt. Okay, suppose the Python environment you had created, what did I mention? PyTorch, anything particular? For example, 2x. Okay. So you have to, you can list the environments also, but if you already remember, oh, this is the environment I had created, you will activate that environment. Okay. Then it's easy. You can say pip install. Okay. And the name of the library. For example, if it says you run the program and it says, I don't recognize CV2, right? So you will open CV Python. You can always Google what is the library for OpenCV. But I'm pretty certain if I take you to, let's go here, software installation instructions, the OpenCV. Yeah, so you can see pip install. Let me see if I can make it bigger. Okay, so pip install OpenCV Python is just in case if you forgot to do that, or down the road we need another library, you will activate that environment, then run the pip install. Then in that environment, it will get installed. Okay. So that will be your typical practice to add more libraries as needed. So coming back over here. Oh, back to the assignment. Okay, it was. Okay, so back to the assignment. Okay, so anyway, hopefully as you go through the code, it will be pretty obvious how we are setting up the training and the test folders and the training and training and test data, right? Okay, I forgot to mention, let me clarify that also. We talked about that the mini batch, okay, where what we do is we divide the data, training data, into small batches. Okay, so we'll pick a small batch out of it. For example, the batch size could be, let's say, 8. Okay, so we'll do the forward pass. We'll go backward. Okay, and compute gradients. So compute and add gradients. Okay, so for example, 8 times, if the batch size is 8, we'll go through, as an example, 8 times and keep adding these gradients, right? And then when we do the update, okay, at that time, we'll divide it by 8 because we want to do the update on the average of the 8 gradients that we have accumulated. And the intuitive idea is one gradient says go this way, another gradient says this way, another this way, right? If we take the average of all of these, that will be a more stable way to move towards the weight that are minimizing the loss, okay? So that gives us more stability in training and results in a better performance. Okay, another concept is, okay, so as I mentioned, the general technique is called gradient descent. So in this case, mini batch based gradient descent. Further, over the years, we recognize that, for example, let's say we have a training data of 1,000. So let's say we have in our assignment number 4, we have 1,000 training data, right? Let's say 0 through 999. So these are images. Let's pretend we've already linearized them into a vector, and we know the expected output for each one of those input images, right? Okay, so now the question is, as we are writing our training loop, okay, one possibility is, and let's pick the example, we said batch size will be 8. So we pick the first 8, we pass it through the model, compute the loss, go backwards 8 times, take the average, update the weights, pick the next 8, pass it through the next 8. Similarly, we go sequentially last 8, okay? So if we just went through all the data one time, the entire training data one time through entire training data. Okay, so that is called one epoch in the technical terminology. Okay, so just training it for one epoch, generally the network, if we stop there, even though we have gone through all the entire training data, it will be okay, but it will still not be the best result, meaning it will not be fully trained. So generally we train it for many epochs, okay? For example, you may notice if you train it for 50 epochs, you get the best model that works best on the test data. Remember, training accuracy does not matter. You have to see the training accuracy should be dropping as you train it. If the training accuracy is not dropping, what does that mean? You have an error in your code, okay? If the training accuracy stays, let's say, 10.23, then 10.25, then 10.2. Every epoch or every batch you measure it, and it hardly changes. 100% your code has a problem, okay? So if the training accuracy is reducing, next epoch it's 9.23, then 8.7. You at least know it's learning, it's adjusting and getting better, right? Okay. So generally we'll train it for many epochs. In one epoch, once again, means one time through the entire training data. Okay. So even that technique over the years, as we have learned how to train these more effectively, does not work as well, okay? So the ideal technique that works best is stochastic mini batch. Okay, so this is the best, proven best, again, experimentally. For training of our network. So what does stochastic mean? The meaning of stochastic in general, mathematics is basically means it varies with time. Okay, here what we mean is if we are following the exact same pattern in every epoch, right? Meaning we fed the first state, then the next state, then the next state. Okay, that is not stochastic. Every epoch, it's the exact same pattern. So stochastic means keep changing the pattern, make it completely dynamic and random. So what we typically do is whatever training data we have, we shuffle it at the beginning of each epoch. Okay, so when we shuffle it, not only we have to shuffle the X, we also have to correspondingly shuffle the expected Y, otherwise it will be a mismatch. So if you take a look at the code, the shuffle is applied to both the X and Y at the same time. Meaning, if, for example, 15th position got moved to the first position, the corresponding Y also will get moved to the first position. Okay, so as we randomize our data, right? Then after the shuffle, we can pick first state, then the next state, then the next state, and the first epoch. Then as we go to the second epoch, we shuffle it differently. Okay, so the first state that are being fed to the network will be different in each epoch. Okay, then the network learns more variety, learns to generalize better so that it can do a better job on the test data, right? So stochastic gradient descent is the best technique. Generally, you will see people saying, oh, what training algorithm are you using? SGD. What does SGD mean? Stochastic gradient descent. And what is stochastic? Meaning we randomize it, the order of the data as we fed to our network throughout our training epochs, right? Okay, so from our learning point of view, like I said, gradually we'll keep making it, more and more informative so that hopefully in one more lecture, you'll know all the foundation of neural networks. Then we can move to convolutional neural networks and to PyTorch so that we are using these libraries. We don't have to do this lower level gradient calculations of ourselves. But like I always say, if you have a strong foundation, even the most advanced concept become very easy. You can see why they work or why they don't work and where can we improve them. I was giving you an example of the three godfathers of AI, right? So one of them is Hinton. One of them is LeCun. Okay, LeCun, in my opinion, was the pioneer with respect to convolutional neural networks, which made a huge revolution in at least the image aspect of field, right? Hinton is the, created the breakthrough in the entire learning of these neural networks, including simple techniques such as dropout. Okay, and the third one is Joshua Bengio. And so he's so all three of them were given the Turing Award, which is the equivalent of the Nobel Prize in computer science, because they don't have a category for Nobel Prize in computer science. So Hinton, if you remember, was given for physics, not for computer science, right? So anyway, so the point I was trying to make is that even at the most advanced level, okay, the concepts are extremely commonsensical, okay? And that's what we are trying to go through and see. All these, calculation of derivatives and so on, nothing complex about it. This is like a high school math, if you took calculus in high school. But you have to understand the intuition behind it. What is it doing? As we talked about, the intuition is if you have a single weight and a loss function, right? The loss landscape could be something like this, like a curvature. It doesn't matter where you started the loss. As you take the derivative, which is partial L over partial W, okay, which is the slope. You want to move this weight towards the direction where it keeps getting, the loss keeps getting smaller, not the weight getting smaller, but the loss getting smaller. And that's why we are doing W equal to W minus lambda partial L over partial W, so that if the slope is positive, reduce the weight, so that next weight will go over here, next will go over here. In case you started over here, now the slope is, or the derivative is negative. So now we are increasing the weight to move toward. So again, a simple concept, that this is how it's learning. Now we added the stochastic part to it. Hey, which also intuitively makes sense, okay? Because if you are seeing the same data in a repeated manner, you won't learn. You want to see all different varieties so that you can learn to do a better job on the unknown data, right? So again, a very, very simple concept, right? Okay, so as we go along, so this is more, more of a informative talk I'm giving you, is that all three of them, in my opinion, if you take a look at their entire work, somebody could argue with me, but I would say everything was so simple. They were not like Einstein, okay? If you take a look at Einstein's theory of relativity, I tried to study it. It is intimidating math, okay? All their ideas, I can relate to it. They are commonsensical, okay? Yet they have made profound, revolutionary, perhaps even more than Einstein. And, you know, AI is going to take over our entire lives, no question about it, right? Okay, so, so we'll take a look at CNN. I just 2 more minutes. I wanted to give you one piece of information about Yoshua Bengio. Okay, so as let's take a look at, for example, from AI point of view. Let me go back over here. What is the most revolutionary thing? Why is everybody is so excited about AI? 5 years ago, there was some excitement, but not to the level it is right now. So what has made that difference? What did you see? ChatGPT, right? Now, all of a sudden, you can see, you can ask it pretty much anything on any topic, okay? Sure, it makes a mistake here and there, but projected to another 2 years, 5 years down the road, it will be doing all our work for us. So you won't need any professors. You'll be asking ChatGPT how to learn, right? So ChatGPT, if you, and again, in NLP course, you will learn this, is based on the idea of transformers, okay? Transformers, again, is a very simple idea. Some of you are in the NLP and the large language model course, where I mentioned that the whole concept of transformers is measuring pairwise similarity between 2 words, okay? That's how it learns, and that's how it learns to predict the next word. So again, very simple concept. One of the pioneers over here was a person named Vaswani, okay? In my opinion, he should be the next Nobel Prize winner, because that's, ChatGPT will not be here if it wasn't because of the transformer architecture, right? Okay. Again, very simple. As if I compare it to theory of relativity, you know, simple concept, but the application is amazingly profound, and it can reason to some extent, right? Okay, so we are learning neural networks right now. In a week or so, we'll be pretty much done with the entire, hopefully 99% of what neural networks can do. Then we'll move to CNNs, then we'll move to transformers. Okay. Just to give you again, a motivational talk, CNNs, or before transformers came, we were trying to, because language is a little bit more difficult to understand as compared to images. Okay, for example, if you have an image of a cat, everybody knows it's a cat. There's no ambiguity, right? If I say there's a word called bank, okay, the meaning of bank keeps changing depending on the context that's being used. It could be bank where we deposit money, could be river bank, it could be sign of confidence. You can say you can bank on it, right? So that is the hard part about NLP. So before transformers came, there was another type of network that we created, and I'll briefly talk about it in this course, hopefully. It's called recurrent neural networks. Okay, and we tried to use it on NLP. There was some success, but then it still did not work, very impressively. Until transformers came, which is even a more simpler concept, and all of a sudden that led to ChatGPT, right? Okay, but like I said, all of these are based on very simple concepts. So let me show you if I have it open. Let me see if this is. So let me go. Okay, so here is the revolutionary paper, which eventually led to the development of ChatGPT, right? So this is the transformers idea, and the title was "Attention is All You Need." Okay, it became very famous. If you see, I think there are like 80,000 citations, which is incredible for one paper, research paper, right? And like I said, ChatGPT, Gemini, Llama, all of these are based on fundamentally this concept. Okay. And like I said, in my opinion, he should be given the next Nobel Prize. Okay. Because ChatGPT will not exist without these ideas, right? And prior to the transformer or the attention, as I mentioned, the RNNs were the supposed revolution, but never performed well. Okay. And now let me show you this other paper, which just came out. Where did it go? Here. Okay. So what's the title? Were RNNs all we needed? Okay. And if I show you who is one of the authors, Yoshua Bengio, right? He's the third godfather of AI. Okay. And so again, in our advanced deep learning, I'll cover this. This was released October 2024. So very, very recent. And so they basically went back to RNNs, just to give you a brief summary of it, and said, oh, if we just change this one tiny thing in it, it actually is much better than a transformer. Okay. So will the next ChatGPT will be based on this idea? I don't know, but I still, because one of my PhD students brought it to me and say, Professor, take a look at this. So, so I'll go through, but we are in an amazing, exciting era. But once again, let me keep emphasizing, don't be intimidated by any of this math, all of this is very, very commonsensical. But the implications, the applications are amazing. So keep learning. We'll, keep making our background very, very solid so that all of these concepts make perfect sense. I'll stop here. Hey, there was a question about midterm, and whoever wants the midterm can stop by. I'll give it to you. I'm joking. I've never come across a student who's excited about taking an exam. So, okay, maybe in a couple of weeks, but keep learning. Don't worry about the exam. Just a second.